So I'd like to thank Avner and Jim for the invitation to discuss this paper. I've long been an admirer of Alexander's work and Adair's work and Luigi's work in this area, and this paper is no exception. There are two primary questions raised by this question. What's the probability that firms are engaging in fraud, including those that are not detected? And what's the cost of fraud? Here are the big number takeaways from the paper. Now, in one sense, my job as a discussant in a narrow sense is easy, because this is the kind of calibration exercise that almost begs for some criticisms. So I'm going to give you some critiques, but I'm also going to, at the end, tell you why I think this is an important exercise and worth considering. So the authors start by exploiting the rule for conditional probability and say, if we want the thing on the left-hand side, and we can come up with some observations that tell us what the probability of firms that firms both commit fraud and get caught, all we have to do is come up with a denominator in this equation. So they start with this baseline number that 4% of firms at any given year are committing fraud, and make two key identifying assumptions that allow them to express the probability of getting caught as the ratio of two observables. They then try to come up with estimates of these observables. These imply that the probability of getting caught is 26 or 27%, and boom, that gives us the big takeaway, the initial big takeaway, that it's 15% of firms in any given year that are committing fraud. So this is not an exercise in testing a hypothesis. This is a measurement exercise. So it's all about the estimates, and I'm going to have comments about this estimation process. So I have comments about the identifying assumptions. I'll have a couple of comments about this 4% number, and then comments about the data that are used, following up a couple of comments that Alexander made about possible sensitivity of these results to the data or proxy used to measure fraud. So first, the identifying assumptions. The first identifying assumption is that before Arthur Andersen's demise, Arthur Andersen clients were just like non-Arthur Andersen clients in terms of their propensity to commit fraud. And the second is that once Arthur Andersen clients are booted out of Arthur Andersen and go to new auditors, the new auditors are going to catch all frauds that Arthur Andersen would never have caught. So I've listed a number of observations or questions about each one of these identifying assumptions that raise questions about the assumption's validity. For example, up at the top, we know that there are huge industry effects. Arthur Andersen was big in the energy sector. We know that there are huge industry-related wave patterns, both in the detection and the commission of financial fraud. There's some evidence, although Alexander cites other papers that counter number 3 up there, that Arthur Andersen clients manage earnings more. You can see that jointly what this suggests is maybe these two aren't directly comparable, that maybe what's going on is that Arthur Andersen firms actually did commit more fraud because of the nature of firms they were. I won't go through all the list under assumption 2, but as an example, a lot of former Arthur Andersen clients simply followed the audit team when the team left Arthur Andersen and went to a new firm. And this raises questions about whether these guys now working for Price Waterhouse are going to suddenly become more adept at uncovering fraud, especially if they're frauds that were ongoing while they were the audit partners previously. So each of these assumptions could be played with quite a bit. The authors do recognize some of the sensitivity of the results to relaxing these assumptions, and something that I think could be done a little bit more. I have a comment about this 4% number. The 4% number up at the top is the fraction of firms in the process of committing fraud in any given year, given the author's data. The percentage of firms initiating fraud in any given year using these data is about 1.43%. The difference in these two numbers represents that if these are steady state measures, that must be that frauds are lasting 2 or 3 years on average. When we're thinking about the fraction of firms that commit fraud that are caught, it seems to me that we're interested in the fraction of new firms that enter the pool of potentially catchable firms every year, not the notion that if you are caught, you're caught 3 times over because you committed a 3-year fraud. And because of that, I think the appropriate number to use is, in the numerator here, is the 1.43%, which represents the number of firms initiating fraud every year. And if you plug in this number, you get a number of different magnitude, 3 times smaller, which indicates that it's not 15% of firms committing fraud in any given year. That's the big takeaway. It's that 5.4% of firms are initiating fraud in any given year. Just a different sense of what the problem is. How about the data? The data that one uses in this calibration exercise are going to affect all of the numbers. I thought I'd illustrate how, by looking at the calculation of the probability of getting caught, by looking at these 2 observable numbers that, given the identifying assumptions, give you a measure of the probability. And to do that, I thought I'd use a different proxy for fraud. Naturally, I'm going to use my data on 13B violations as prosecuted by the Securities Exchange Commission and Department of Justice for financial misrepresentation. So I used the same filters that the authors use and find that the fraction of Arthur Andersen firms that were committing fraud in this period before the meltdown and that were caught in the period after the meltdown is 4.6%, which is a bigger number than you get using the proxy that is used in the paper, which is taken from the Stanford class action securities class action database, which is going to capture just simply a different indicator of wrongdoing. Now, if you look at non-Arthur Andersen clients, it turns out that 3.8% of these non-Arthur Andersen clients were committing fraud before the meltdown of Arthur Andersen and were caught after the meltdown. So in other words, the gap between Arthur Andersen and non-Arthur Andersen clients that are subsequently caught is much smaller using this different proxy, this proxy which actually is catching more indicators or instances of misconduct. And if you plug in those numbers into this exercise using all the other assumptions, you'll see that the ratio of these probabilities is going to be different, and it implies that the probability of getting caught, given the identifying assumptions in the paper, is 82%, not 27%, implying that the probability that a firm year is a fraud year is not 15%, but more like 5%. So again, here just the data used can have large influences on one's estimates. I'd like to talk a little bit about this cost estimate, whereas my previous comments are more about sensitivity of the analysis and the number that you want to take away to different inputs into the process, something that I think the authors are very sensitive to. This is more a criticism of what the notion of cost is. This is a schematic that represents how cost is calculated, cost of fraud is calculated in the paper. So this is a hypothetical case in which during the fraud period, firm's value goes down. This value at the end of the fraud period is compared to a hypothetical counterfactual, which is constructed using changes in industry multiples, and the average cost of fraud for firms engaged in fraud is estimated to be 20% of enterprise value. Now, to see how this might play out, I pulled a case in which a firm was caught for fraud. This is a classic case of fraud involving Xerox, which in early 1997 started to cook its books by accelerating the revenue, the recognition of revenue from lease contracts. In late 1999, the first class action lawsuit for this misconduct was initiated. And if we were to go through the same type of exercise as in the paper, you would see that I've drawn in this green dotted line the counterfactual based on industry multiples, and this purple bracket represents the cost of Xerox's fraud as measured in this paper. But what's going on here? Well, it turns out that there's first an identification of the fraud period issue. So they're both on the beginning and the ending dates for this fraud period is going to be affected by institutional factors. For example, in the beginning, it's typical that class action lawsuits are constrained in the identification of the violation period by rules that affect the class period, how far back in time specifically you can go in launching, say, a 10b-5 class action lawsuit for misrepresentation or fraud. If you look at corresponding SEC releases for the same instances of misconduct, frequently you see the violation period is identified as going back much farther in time. On the other end, it's typical that the initial class action lawsuit filing date happens well after the fraud period actually ends. It certainly happens after the initial revelation of the fraud. In the case of Xerox here, the difference between the initial revelation, as I'll show in a moment, and the first class action lawsuit was 2 months, but it turns out that on average it's closer to 5 months, 150 days. So again, identifying the period over which you're going to measure these changes can be important. But I think more important, and as identified by that discussion, what's going on is that, as shown here, before the lawsuit filing, there's a big stock price decline that came when Xerox basically revealed that it was sort of cooking its books and revealed that third quarter earnings in 1999 were going to be shorter than forecast. What this illustrates is a general and pervasive tendency in these cases for the decline in value that is being counted as a cost of fraud as really being not a cost of the fraud, but it's the cost of the revelation of fraud. So you can think of a lot of cases in which fraud that is not revealed may have zero positive or negative cost. Let's say, for example, Xerox was able to grow its way out of this accelerated revenue recognition accounting problem. The cost of the fraud may be zero. What if there's an instance of say, a 3-year fraud in which the net effect is that managers are able to boost compensation compared to otherwise? Well, that involves a transfer from shareholders, but if that's the only effect, there's no cost of the fraud. If that fraud subsequently is revealed, as this paper and other papers have shown, then you do see large value declines, and the large value declines have to do with various things such as the penalties that these firms face and the reputational consequences as their counterparties change the terms with which they do business with these fraud firms. So I think I'll skip this because of time, but the big takeaway here is that this measure of cost of fraud is really a measure of the cost of the fraud being revealed. And I think it's worth thinking through what the cost of the fraud is. And cost of the fraud to the firm, cost of the fraud in a social sense are going to be two very different things. Why is this paper nonetheless compelling? So I have some criticisms, some suggestions about this calibration exercise, and then a criticism of the cost estimate in particular. Nonetheless, I think this is a very important paper, and it's important, an important exercise that should be considered. And the reason is that it grapples in a really creative way with this Arthur Andersen identification with what is a large elephant in the room in fraud-related research, which is that we're only considering the tip of the iceberg, as Alexander pointed out. Now, why is this itself important? Well, I think this is important because fraud-related investigations have an unusual opportunity to gather or show insight into what I think of as the dark matter of economics. So fraud is interesting in and of itself. You know, we all like a crime story. It's an important phenomenon, much like capital structure or the structure of financial market. These are good reasons to study fraud, but I think an additional reason is that it provides some insight into how, when, and why trade does, or importantly, frequently does not collapse because of the lemons problem. If you think about it, there are billions of transactions that go on every day around the world. Most of these transactions are not characterized by opportunism or fraud on the part of one counterparty or the other. Why is that? Well, we have stories and theories dating back to Adam Smith, speculating about culture and reputation, encouraging honest dealing, despite the fact that each counterparty knows that he or she may act opportunistically. But we have very little data about it. And one reason we have very little data is we don't have measures such as the measures provided in this paper. So to summarize, what this paper does and why I think it's an important paper for us all to consider is that it highlights this tip of the iceberg problem, provides a clever identification strategy to estimate the probability that firms are committing fraud and the probability that they're going to get caught. These probabilities are important for things such as determining optimal penalties, for fraud research, evaluating policy, and most importantly, it's a step toward gaining insight into instances in which the various things that we think are important in encouraging honest dealing break down and therefore provide some insight into where the lemons problem works or doesn't work. I need to stop, but I thought I'd tease you with a Dilbert cartoon on fraud and the lemons problem, because this, in fact, is the best short summary of what the problem is. I thought I won't read through this, but here are these guys trying to do a business deal. They can't trust each other to work through the contract. They can't trust any third parties. And the final caption is, and thus ended capitalism. So I think what Alexander's work is doing is working at and trying to get a handle on why this isn't the equilibrium outcome by finding and identifying cases where there are breakdowns, such as illustrated by the cartoon.